Let's talk about phase change. So here's how you use this video. On the screen, during the slides, there will be green highlighted text. If you're using this to take a notebook, that's what you should be writing down. Now, throughout the video, there's going to be blue text. Those are questions for you to consider or for you to practice the material. And throughout this code, there's going to be two codes. There's going to be one that's a visual code that shows up on the screen and one that's a verbal code said by myself. They can happen in any order, so pay attention. Let's get started. So first let's go over the states of matter. So let's look at solids. A solid has a definite shape, meaning it's rigid, has definite volume, does not take the shape of their container. It is the most dense state of matter, and the exception is water. Solids are well organized and are difficult to compress. In solids, the particles are fixed and do not move past each other. And there are different types of solids. So an amorphous solid is any solid that is not crystalline. So we've got amorphous solids and crystalline. And what I want you to see is that in amorphous solid, those particles are not in a repeating pattern. So if you look to the right over here, there's like a crystalline solid. There's a repeating pattern. And then you've got amorphous solids, and the atoms vibrate in place, more random arrangements, and examples of this would be like glass, plastic, wax, and silly putty. But really what we need to know is what solids are. You can see this zoomed in image. Those particles are really close together. It's the most dense, and the exception is water. And that brings us to the question, well, why does ice float, right? And if you look back there, it all has to do with the fact that when ice forms, right? So we've got water, H2O, that's in a liquid form, which we're going to get to. With the ice, though, is it becomes like this crystal, right? And it forms this crystal, and it's dense, and it holds space in between that. That makes it less dense, and that is really the exception. So, but you should know that solids normally are the most dense state of matter. Now, let's move on to liquids here, right? So liquid has no definite shape, it's not rigid, has definite volume, and does take the shape of their container. Liquids are less organized, difficult to compress. In liquids, the particles slide past each other. And the one property that I want you to know about liquids is it's called viscosity. It's the property of a liquid that describes how fast or slowly it will flow. So if we look over here, it's resistance to the flow of fluid. You can see that water is going to pour more quickly than honey. Honey has a very high viscosity. But if we look up here, let's just talk about liquids. You can see here it doesn't have a definite shape. It has a definite volume, and that means that if I pour it into a different container, it's going to still have the same amount, right? If you take a drink out of the refrigerator, pour it in a glass, you don't have any more or less of it. It just takes a different shape, but you have the same volume, and it does take that shape of the container, whatever you pour it into. Now let's talk about gases. Gas has no definite shape, right? Meaning it's not rigid, no definite volume, does take the shape of their container. It is the least dense state of matter. And you can see that those particles are far spread out. Gases expand to fill their container, and they are able to be compressed. So this is the one that can be compressed. Gases have very little organization because the particles are widely spaced and randomly arranged. In gases, particles bump into each other. And vapor. A vapor is a substance that is a gas, but it's usually a liquid or solid at normal room temperature. The example is like water vapor, like the water that's in the air. Even though it's room temperature, it's still in that gaseous state. We just call that like vapor, like water vapor. And if you notice, like what I want you to see is like what sets it apart is the fact that it fills it has no definite volume. It fills the container. It expands to fill that container that it's in. That's what sets gases apart from the other states of matter. Now let's talk about the fourth state of matter, plasma. Plasma is that fourth state of matter. It is super hot electrically charged gas where atoms lose some of their electrons. Now, plasma can glow and be affected by electric and magnetic forces, unlike regular gases. This is what sets it apart. If you can see this little graphic over here, you add enough heat energy to it, you're basically stripping those electrons away, and it becomes this electrically charged gas. Plasma makes up 99% of like the visible universe. It is the most common state of matter because like like stars are plasma. They're like superheated gases. Stars like our sun are made of plasma. Lightning, neon signs use plasma. So yeah, it is the most common. It's that fourth state of matter. You just keep adding energy, and eventually you are going to get plasma. So I already talked a little bit about energy here, right? Energy is the capacity to do work or produce heat. So if energy is added, the particles move faster and matter expands. At this time, I'll go ahead and give you the verbal code. The verbal code is 141. I say that again, it's 141. If energy is removed, the particles move slower and matter contracts. They get closer together. Now, adding or removing heat energy will eventually cause a phase change. So you can see this little phase change diagram over here. So you can see I'm either adding it or adding heat energy or removing heat energy. Eventually, it's going to cause you to go from solids to liquids to gas, or gas, liquids to solids, or the two that you might not be so much familiar with is going from solid to a gas, or gas back to a liquid. But you can see up here, like as I add energy, those particles are moving faster and they are going to expand. But then you can get a phase change, right? You go from different states of matter. So a phase diagram is a chart that shows the conditions for a substance to undergo a phase change based on temperature and pressure. So yes, we add energy, but also the pressure that it's at also has an effect of what phase change. This shows why dry ice, so frozen carbon dioxide, undergoes sublimation at room temperature. So sublimation is that one that goes directly from solid to gas. And you can see that on the right over here, that little graphic. It's just basically going directly from solid to the gas, and it's because at normal room temperature, it's not at that pressure to be able to go to liquid carbon dioxide. Now, if we look at these, you can see that there's temperature on the x-axis, pressure on the y-axis. We have solids, liquids, gases. You can see those six ordinary phase changes, sublimation, deposition, vaporization, condensation, melting, and freezing. But there is a point, the triple point. That's where they all meet. The triple point is the exact temperature and pressure where a substance can exist as a solid, liquid, and gas all at the same time. So you can see that the little graphic below that, that's the triple point. You can see there's the solid, liquid, and it's boiling all at the same time. So that's the triple point. There's also a point on this called the critical point. That's a spot on the phase diagram where the liquid and gas phases become the same. So that's really high temperature, really high pressure, and it becomes a supercritical fluid. Now, I've been talking about energy and heat energy, and I want to distinguish between temperature versus heat. So temperature is a measure of the average kinetic energy of those particles. Objects do contain temperature. Temperature is just the motion of the particles, and you can see that little graphic off to the right. You can see the particles are moving, right? The hotter it is, the faster those particles are going to move. Now, heat is the type of energy that is transferred between substances. So it can affect temperature, but they're not the same thing. Objects do not contain heat. Heat is the transfer of energy. Heat naturally always flows from hot to cold objects, and they're not the same thing. So here's the example. We actually do not feel temperature, we feel heat. So let's just take a look at, let's just say you heat an oven to 400 degrees to cook a pizza, right? And the air in the metal rack are going to be the same temperature. They're at 400 degrees. Now, let's just say you put you open the oven, you put your face in there just to check, and hot air hits your face. Well, yeah, you're going to step back a little bit, but you're not going to be horribly injured. But if you grab the metal rack, you are definitely going to feel that's going to burn, even though they're at the same temperature. But what happens is metal conducts heat better, so it's going to transfer a lot more heat energy to you more quickly, so it's going to hurt you more, right? And you don't have to necessarily do this with an oven. If you touch something touch something that's metal, and then touch something that's like wooden or plastic, well, the metal is going to feel colder, even though it's at the same temperature, right? Even though it's at the same temperature, and it's because, well, that metal is taking the heat away from your body quickly, and it's feeling colder. But you do not feel temperature. You actually feel the transfer of heat. So now that we've talked about transfer of heat, there's two types of energy changes or energy exchanges. An endothermic change is when heat energy is being absorbed. It enters, like ice is melting, right? And I like to think of it, right? So endothermic enters, it's entering. Exothermic change is when heat energy is being released, right? So heat exits, right? So here's how I like to think of it, right? I'm a person. If I'm looking at endothermic, right? Heat is entering me. This is me touching something hot. That's what I'm feeling. So I touch the stove. Okay, great. That is that is the heat energy being transferred into me. It's entering me. That is endothermic for me. Now, exothermic would be me touching something colder, like if I touch something like ice. Ice, well, my heat is going to exit me. That's exothermic for me. So now let's talk about phase change energy. This is one of the last things we have to talk about here. So phase change energy is the heat absorbed or released by a substance during a phase change. So you're going from solid to liquid, liquid to gas, etc. Those six common ones there, instead of causing a temperature change. So phase changes happen at a constant temperature. It actually takes energy to change states of matter because it takes energy to break or form those intermolecular forces. So if you look at this little graphic over here, you've got water and you've got gas, you've got those intermolecular forces that heat energy needs to be break those bonds. That takes energy. So if you heat something up, like if you measure the temperature of water, like if you have ice water, you place it on the stove, and you measure the temperature, what you're going to see is that, well, yes, once that ice melts, it's going to take energy to break those intermolecular forces, and then it's going to be a liquid. So all that ice will melt. And then that you add heat energy. You put it on the stove. It's going to be that heat energy, and it's going to increase the temperature until you reach that boiling point. Now, once you reach that boiling point, then all of that heat energy that's from the stove is going to breaking those intermolecular forces, and once it's going to stagnate until all of it is a gas. So that phase changes happen at the same temperature. So let's just get some practice here, right? So let's take a look at these common six phase changes here. We got melting, vaporization, sublimation, condensation, freezing, deposition. So for all of these, I'm going to help you out with these, right? Identify the starting state of matter, ending state of matter, whether heat was added or released, and whether it is exothermic or endothermic. As a bonus, give a real-world example of each. So I'm going to help you out with all of these, right? So melting, this is on the chart, right? So basically, like melting is the first one. It's going from a solid to a liquid. Now, the next one says whether heat was added. So the arrows tell you that. If you look at the top one, adding heat. So heat is being added. Now, if you look up at the top, the arrow, this arrow right here, right? If you're moving in this direction on that phase, the phase diagram, it is going to be endothermic because heat is entering that object, right? It's like I put an ice cube on the stove. Well, heat is entering that. If it's going this direction, it is endothermic. It is endothermic, right? So these are and giving a real world example. Well, we'll go ahead and just move on to that next slide, and it does have some real world examples for that. So let's see, there we go, perfect. All right, so here is some recognition, right? So these are 6 phase changes here, right? Ice is left out on the counter, turns to water. Well, that is going to be melting, right? Because you're going from a solid to a liquid. And you'll be able to determine whether it's endothermic or exothermic based on the direction of that heat. Frost forms on the window on a cold day. So this is going directly from gas to a solid because it's actually that water vapor in the air gets frozen on the window. And, I'll put this up here. That way we can see it. Water is left in the freezer and turns to ice. So that is freezing, right? We're going from a liquid to a solid. Wet clothes are left out to dry. So I've got liquid like in the clothes, and then it turns into a gas. That's vaporization, right? I'm drying it out. Now this one, solid dry ice is left out on the fog and comes off it, right? This is going to be sublimation, right? So frost forms on the window on a cold day, that was deposition, right? I'm going straight from gas to solid, but solid dry ice, you can see that little graphic there. I'm going straight from a solid to gas, that is sublimation. And this one happens to, I know this one, a lot of people experience this. The bathroom mirror has liquid drops on it after a hot shower. Well, that one, you're going from gas to a liquid. That's condensation. That's what happens to like a cold drink when you leave it out. That's why there's water. It's condensation, right? That's what's happening. We're going from a gas, that water vapor, to a liquid. Now, the last two that we need to talk about, because we talked about plasma, we need to talk about ionization and recombination. Ionization is when energy is added to a gas, turning it into plasma by knocking electrons off atoms. And lightning, neon signs, and the sun are all made of plasma formed by ionization. And recombination is when plasma turns back into a gas when it cools down and loses energy, causing free electrons to reattach to ions. An example would be the glowing colors in the aurora or the northern lights come from recombination in Earth's atmosphere. So, but this only happens from the gas state, and this is only with that fourth state of matter, plasma. So just as a final thought, remember there is too much unknown in the universe to take a break from learning. Get out there and question everything.